Okay, today and the next few lectures, we are going to be focusing on what I call the operator formulation of, 2D CFT. So as I write here, we have looked at so far at 2D CFTs mainly through word identities and OPs. And these OPs were always implicitly inside these endpoint functions, and we didn't use any operator formulation. Everything was in principle derivable from path integrals, uh, and it still is, okay. But the Hilbert spaces and operators provide a nice, useful way of trying to understand CFTs. And now what we are going to do is we're going to turn our attention into this. So, so first off, we want to understand what radial quantization is. So first thing that we have to do is that, whenever you speak of an operator formulation, this is going to distinguish, the time direction from a space direction. Although, when we are in sort of Minkowski space times, it's very clear that there is. So, for example, if you're in d dimensions, ds squared becomes minus dt squared plus dxi squared, right? So the time direction is very clear here. There is a sign here which distinguishes the time direction. But when you are in Euclidean spacetimes, so if you do not have this, then your spatial direction and your time direction become sort of on an equivalent, it becomes sort of equivalent. And then it becomes a bit, arbitrary, about what exactly you mean by time and what you mean by space, and how you can distinguish between one and the other. So, so what we are going to do is, in order to make the choice more in keeping with what Minkowski point of view is, what we're going to do is we're going to define our theory on a cylinder. Okay, so look at this, for example. So we're going to actually define this on a cylinder, like we did last time. We spoke about the transition from the plane cylinder to the plane. So what we are going to be doing is, there's we also, we are going to sort of curl up our spatial direction, and the time direction is going to run along the straight side of, of this cylinder, if you wish. You obviously do not want your time direction to be, a circle or something. You don't want closed time like curves. So the uncompact sort of direction is your time direction. That sort of naturally distinguishes between what your space direction would be, which is now identified, and your time direction, which is unidentified. Okay, so we're going to naturally define things on a cylinder, and the and time here goes from minus infinity to plus infinity, as I say, along the flat direction of the cylinder, while the space is identified. So x goes from 0 to l. Okay, so if you want to continue to Euclidean space, we can describe all of this by a single variable xi, which we will call t plus ix. And now, as we did before, what we're going to do is we're going to map this particular cylinder onto the plane. And if we explode it, if you wish, on the plane, then the mapping that you want to use is z is equal to 2 pi xi by l. If you make l equal to 2 pi, then your life just simplifies as z is equal to exponential psi. But let's keep the L nonetheless. So notice that if you want to go to the remote past, in that case, this is going to be situated at a z equal to 0. Okay, so that's clear from the map. You can just put these guys in. And so remote past is z equal to 0. So if t was remote past will be somewhere here. So that is essentially that goes to this point, z equal, z equal to 0 out here. Okay. And t equal to plus infinity maps to the point at infinity on the Riemann field. So when I say that we are exploding the cylinder onto the plane, it is not quite true. We are also including the point at infinity, so it's more the Riemann sphere than the complex plane. So let's just keep that in mind as well. Okay, so now what we'll do is we are going to assume the existence of a vacuum state 0, and upon which a Hilbert space is going to be built, and this is going to be built by applying analogs of what we'll call what the creation operators will be. As you know well, in free field theory, the vacuum is defined as a state that is annihilated by positive frequency parts of the field. For an interacting field, what we will do, the assumption would be for an so that's so for a free field theory, the vacuum is going to be defined as a state which is annihilated by the positive frequency part of the field. So you expand the field in its usual sort of creation and annihilation operators, and acted on this state. And in that case, the part that particular thing, the vacuum is going to be defined by the positive frequency parts acting on that field equal to 0. Now, for an interacting theory, our assumption will be that the Hilbert space stays the same and the energies will just shift. Okay, so that would essentially mean that when we go to t equal to plus minus infinity, the interactions will fall off, and in particular, we can define some in states, which will be a limit of t going to minus infinity of phi of x. Okay, this is going to be free. All right, so that's our usual notions. Now this, within the context of this radial radial quantization. So also notice something which I didn't really emphasize here. So when you are looking at circles, so if you're looking at circles T1 and T2, these are going to be so as we saw, right? As we saw, minus infinity maps to this this point 0 here. So as you're going in, so for each t you are actually going to get some circle out here, and as t increases, the radii of the circle will increase. So by radial quantization, we are going to mean this essentially. Okay, so we are here the time direction is in a sense replaced by these guys. So equal time slices are equivalently circles of obviously constant radii on the z plane. Okay, so that's something that we want to stress. Now, what this means is, so when we are saying that where if you have phi in and that at t equal to minus infinity, that is defined in this way. Within this particular context of radial quantization, that will mean that your in states are now defined by this field phi of z and z bar acting on 0, and you need to take this limit of z and z bar going to 0. So that is going to be your asymptotic in state. Okay. Now you have defined an in state. You also want to define something like an out state, right? So for this, you need to define what a Hermitian sort of conjugate of this particular field is. So Hermitian. So let's try and do that. So one needs to define an inner product on the Hilbert space. And what I'm going to do is I'm going to define a quasi-primary field of H and H bar, and the Hermitian conjugate of this field is going to be given by this equation. So what's funny about this equation is that notice that there is a z bar which sits here with the h, and there's a z which sits here with the h bar, and you notice that z has gone to 1 over z bar and z bar has gone to 1 over z. Okay, a priori this looks absolutely bizarre, and you don't know what sort of the justification of this is. So let's try and do this. Okay, in usual Minkowski spacetimes, Hermitian, Hermitian sort of, conjugation of fields does not affect this space-time, does not affect this space-time coordinates themselves, right? So t is going to stay as t, x is going to be x. But remember that when you're in Euclidean space-times, tau is actually it. So if t remains unchanged, then what you have to do is, because of this factor of I, you need to make sure that tau goes to minus tau, under this, okay? Now tau goes to minus tau in terms of z is just z going to 1 over z star. And if you want to do this for the real surface, then z star is equal to z bar, okay? So that sort of justifies why a coordinate z out here has gone to 1 over z bar, and why coordinate z bar has gone to 1 over z. Okay, so that's one part of it. Now, why do we have these weird prefactors? So let's do that. Let's try and understand why these prefactors are there. And this, at the end of the day, what we'll see are there to make sure that the asymptotic out states and the in states will have a properly defined inner product. Things will not blow up at the end of the day. So how do we ensure that? So let's see this. So as I said, so the out state is going to be defined as the Hermitian, Hermitian conjugate of the in state. So let's look at phi out and phi in. Okay, so this is z bar and omega bar going to 0 of this guy, right? Now you have this phi dagger here and phi here. So we are going to define things in the usual way, in the way that we have done before. So phi dagger of this guy is going to be given by an expression like this with these prefactors in front of it. Okay. Now notice that you have 1 over z bar and 1 over z, where while these z's are actually going to 0. Okay, so this is actually becoming singular. All right, on the face of it, this is something singular, but let's see where it leads. Okay, so omega and omega bar equal to 0 is something that you can do in a straightforward way. There are no factors of one by omega hanging around, so you put this equal to 0, and we will just have something like, so we will say that z is equal to 1 over xi, and z bar is 1 over xi bar. So if we do that, then what happens is that this limit becomes z bar, xi bar to the twice h, xi to the twice h bar into this guy. Now this is phi at xi bar and xi, and phi at 0 and 0. So you remember that what is going to happen is this is going to give you, so this at the end of the day is, as you notice here, it's a 2-point function. These guys are quasi-primary fields, and what we know from before is that this has to go like xi to the minus so the first thing is xi bar, so xi bar minus twice h xi to the twice h bar, right? So that is what this guy is, and there is some C12 which multiplies this. So you see that what happens is when you take this limit of xi and xi bar going out to infinity, all you are left with is this is equal to C12, right? So this is so the fact that you had these weird factors in front made sure that this particular sort of, I mean, inner product which you had made sense at the end of the day. This gave you a number at the end of the day. Okay, so this expression is independent. So you know, let me sort of erase these things that I've written down here. Okay, and also let's get rid of this. So what happens is that if you so you know, essentially this is what I write here. Given the form of the conformally invariant two-point function, this expression is independent of psi. So that is why you have to have these prefactors. Okay, I mean, otherwise if they had been absent, this would not have been well defined in the limit of xi goes to infinity. All right, so what we have learned in this part is that, you know, when you have a field, if you look at its Hermitian, I mean, Hermitian conjugate, you have an expression like this, and you have to take care of these factors in front, and you also have to make sure that you remember to replace z by 1 over z bar. Okay, so that's the thing about Hermitian function conjugates. Now, next, what we want to be doing is we want to be looking at mode expansions. Okay. So when we have a field of phi of z bar, which has dimensions h and h bar, what we will do is we will expand this in terms of modes phi mn as the following. This, okay. So this, I mean, equivalently means that you look at you know, you can I mean, transpose this, I mean, this uh, particular relation, and so that would mean that phi mn is given by this. Okay, so right now let's do something. Let's try to take the Hermitian, I mean, Hermitian's sort of conjugate of this now. So in a straightforward way, that will just replace z's by the z bars, and z bars by the z. So this is the expression which you have. Okay, so you have a phi dagger as well. If we were to I mean, understand what, sorry, this is not mn, this had to be phi of z bar. Just give me a second. Phi dagger. All right, I mean, that's probably also not a good thing to say. On the other hand, we have just shown that the right way to try and do this is by you know, this is what it is. So you should have these prefactors, and you should have phi is this. So now let's expand this guy out. What is this? So this is again what you have is now you use the fact that you want to you know, this is your, I mean, expansion. So in a similar vein, you can expand out phi mn like this, where your z bar now has m plus h and z has n plus h bar. Okay, So now 4.6 becomes a sum over, so you can exchange, I mean interchange. So this is summed over all integers. So you can also just relabel them. That is what I've done here. So this is phi minus m minus n and these expressions, let's say. What you do is that, so this expression 4.5 and this expression 4.6 have to be the same. So what you see from here clearly is that phi mn, phi minus n and phi, so phi dagger mn just flips the signs here. Okay, that is what you see. So this is what you get at the end of the day. So what we are going to be doing from now on is we are going to be sort of dropping the anti-holomorphic part, and so we are just going to expand the phi of z's we're going to expand not phi of z bar, but just the z part of it. Okay. So yeah, this is something that is going to be happening for most most cases as we go along. And this holomorphic factorization, as it is called, means that you have an equivalent barred sector which you just add on to this. Yeah, so that was that for trying to get these two things out of the way. Now we want to say a little bit more about operator ordering. Before that, let me just stop and ask you guys if there's any questions so far.
Hello, sir.
Yeah. Yes.
Can you go back a little bit?
Sure.
The previous page.
Previous page.
This mode expansion that you wrote down.
Yes.
Can you just justify this again? This 4.4.
So we are expanding this in some modes.
Okay.
I don't know what sort of justification you would want for that. I mean, it's just think of this as
is this a kind of Lorentz series? Is this something that can be derived out of Lorentz series?
You could think of it as that. Yes. This is
Okay.
Yeah. This is it's just the fact that you have these the z and z bar pieces usually in our sort of complex analysis. You don't usually see a z bar piece out here. But yeah, so that's something that you could just do. And in any case, we're just dropping one. There's the the z bar pieces, if you wish. So yes, it's just and
so
just an expansion like
it seems like Lorentz series.
Yes, that's true. But we are also doing a little bit more. We're just trying to also figure out. So remember, yeah. So so that's the thing. The power of CFT in 2 dimensions is sort of it sort of boils down to the fact that you can use a lot of your known sort of complex analysis tricks out here. So this is exactly like a Lorentz series.
I want to make a comment.
Yeah, sure.
So the expression for this mode expansion can be seen more transparently if one transform from plane to cylinder, and then it can be interpreted as a Fourier series on the cylinder.
That's right. Yes.
So
yes.
That I think is more transparent.
Yeah, you could. So this is if you could obviously do that as a there you have explicitly an S1, right? So there you would be able to sort of break into sort of Fourier modes as well. Yeah.
Sir,
does that make things a little clearer?
I will look into it on my own.
Okay.
Sir?
Yes.
Yeah, so in this operator formalism, we have defined states, right? operators and also states, but
Yes.
we have not said anything about evolution of those states. So how will that happen?
Yeah, we will see that, but as you can see, so what is happening if you just look back at this particular way of trying to define it. So what you do is you're going to insert something here. You're going to insert something at the, I mean, asymptotic past, which is this point, and then you are going to evolve it in this sort of if you are looking at what is going to be the time evolution. This is something that we have not done, but we will do. What you can say is, I mean, let me just say it right now, since you asked this. So let me so as you know, I mean, Hamiltonian, if you wish, is Hamiltonian on the cylinder, which is what we are interested in. Is what this is sort of, I mean, time translation, right? So this is sort of, I mean, del tau, right? Del
Yeah.
del tau, yeah. Uh, so now, what happens is that you have this map. So you have z is equal to e to the xi, right? So z is, let's say, I just always mix these things up, t plus ix, and this is e to the sigma plus I tau. So if you do this map, what you will see is that del tau on the cylinder, so maps to uh, you know t del t plus x del x. This you would recognize is the d operator. So Hamiltonian on cylinder, Hamiltonian on cylinder is equivalent to dilatation operator on the plane. Okay. Now, you would remember that what were we doing earlier? We were labeling things. So we said that if you so you had some particular operator p, and you are going to sort of look at delta of p, right? So we were going to sort of always label our states by this. So this, as you can see, is equivalent to sort of looking at a, I mean, sort of, I mean, this is the equivalent of looking at energy eigenstates. So this is what we will see a bit more clearly as, I mean, as we go along. In the 2D CFT case, what we will see is that we will have things which are labeled by so this is going to be equivalent to, so D is going to be equivalent to L naught plus L naught bar. We will see all of this, and we will see that we will have states which look like this. So H bar is going to give you H of H bar, and you'll have L naught bar of something which is H bar, which is going to give you H bar of H bar. So we will look at the, I mean, sort of we'll look at sort of the equivalent of energy eigenstates, and we will build things from there. Okay, so we will build, I mean, we'll build our Hilbert space from there. But just hold on a little bit. Okay, we will try and make this a little clearer. We also did a little bit of this when we were trying to look at some particular operator OP at xy, I mean, sorry. So when we were looking at this earlier, when we were looking at something like xt, right? So we had this e to the iht minus pixi O of 0, 0, e to the minus iht, so this is an I plus I pixi, right? So we were looking at, so the, I mean, evolution of these guys are done through things like this. So you can translate this onto the, plane in the two-dimensional case, and yeah, we will see how to do this. Okay.
So, and one more thing,
Yeah, sure.
uh, about the vacuum for interacting theory.
Mm-hmm.
In QFT, generally the vacuum is different, right? For the free theory and interacting theory, but we get the vacuum for interacting theory through the Hamiltonian and going slightly in the imaginary time direction, right?
Mm-hmm.
Uh, so, are we going to do the same thing here also for the interacting case?
Um, okay, so from the point of view of the symmetries of the theory, the vacuum is going to be actually, so we will try and I'll try and make this a little more clear. So the vacuum of the theory is going to be defined in the same way. So we are actually not going to, say much about whether or not. So the main difference in sort of the approach is that in in a field theory, we explicitly depend on what our Lagrangian or our Hamiltonian is, right? We are trying to build a sort of interface whereby what the main inputs are going to be the symmetries of our theory, right? So we don't necessarily do the same thing. What we will do is we will try and define what the vacuum is. So we are going to be defining the vacuum through the symmetries of the theory. So what we will do is we will define a vacuum zero such that this guy is going to be annihilated by yeah, okay, so I'm actually going a little bit ahead of what I want to do, but L minus 1, L0, and L1 acting on this. So these things are going to so L minus 1 acting on 0 is going to give you 0, L naught is acting on 0 is going to give you 0, L1 acting on 0 is going to give you 0. So this is going to be how your vacuum is going to be defined. But let's hold on a little bit more. So it's not quite the same, and we are not going to sort of distinguish between if this if a CFT is free or not in the same way as I wrote in this last slide. So what we will do actually is so what we will do is the assumption will be that the Hilbert space stays the same, and just the energies will shift. Okay. So let's see this. Let's try and go ahead a little bit more and see what we want to say by this. Okay, so let's
I
hold
have
on.
a question, just
Yes,
like following up. That
yes, yeah.
that assumption, doesn't it make unitarity obvious?
Which one?
The Hilbert space stays the same for the interacting field theory as well. So phi in and phi out belong to the same Hilbert spaces, and unitarity is obvious, right, from this assumption.
You will see that unitarity gives us some more. It's there is something more that you have to do as well. You'll have to make sure that the norms of the things. I mean, if you want to make sure that you do not have sort of negative norm states in the game, you will see that you have to put some bounds on what your so what are we trying to do? What we are trying to replace the usual sort of data, if you wish, what the Hamiltonian is, or what the Lagrangian is. So for example, you could have added I mean terms to your Hamiltonian, which would make the things unbounded, right?
Right, right.
Yeah, so if you were to let go of those things, so we are trying to sort of repackage it into something else. We are trying to repackage it into something which is going to be dependent on what the weights of the primaries would be and what the central charge of the theory would be, and that in itself is going to give you the whole deal. So now you will see that by by demanding, for example, that the norm of states in the in a particular theory has to be greater than equal to 0, we would be able to derive some bounds on what H and H bar and C could be. So
Okay.
so it's not quite the same. So I'm saying, as I'm trying to emphasize, the language is not quite the same. The emphasis is more on symmetries than on particular systems. And so we will try and push this. I mean, as you guys have already seen, a lot of things. I mean, one can say lots of things about it, like, you know, 2-point functions, 3-point functions here. I mean, yeah, I mean, I don't know how much I would be able to do of it, but there are things when you're looking at 4-point functions called conformal blocks, which you heard about a little bit in the you know, the bootstrap introductory things yesterday. So there are things like that. So, you know, it's repackaged in a way which makes symmetries the center of your sort of program, if you wish, and we will try and you know, build on that.
Yeah. Okay.
Yeah. Okay. So long-winded replies to questions. So let me just skip that page, and okay. So we have you know, we have defined in the products and mode expansions, and yeah, I mean, as was being said, so this is a sort of I mean, like your LoRa expansion. Uh, you need to keep in mind that these are going to be operators and so on, but let's, I mean, you know, it's going to be a quantum system as we, I mean, as we go along. But the central theme is I mean, a lot of the sort of you know, complex analysis that you have learned earlier will be useful here. So this is again, so as I mean, almost also tried to point out, you could try and you know, take this and map it onto the cylinder, for example. There you have a, I mean, compact in circle direction, and these modes in that case will turn into your Fourier modes. So yeah, so that's one way of trying to see this. Now we get into the important question of, I mean, operator ordering. So as I write here, so it's important to notice that under this cylinder, I mean, plane to rather cylinder to plane map, the constant time slices on the cylinder become circles of increasing radii on the plane. So within radial quantization, time ordering that appears in this definition of these, you know, endpoint functions becomes something which is a radial ordering. So think of this as, so you have done you've learned about time ordering in your usual quantum field theory course. Now this is radial ordering, and what is going to happen? So if I have this, I mean, curly r out here, that would mean phi 1, phi 2, phi 1 of z and phi 2 of omega is phi 1 of z, phi 2 of omega, as long as mod z is more than mod omega. And if mod z is less than that, what happens is that the, I mean, order is going to change. If you're dealing with fermions, there is going to be an extra sign in front of it just to account for the anti-commuting nature of the fields. Now, since all the fields within some endpoint functions must be radially ordered, so the left-hand side of any OPE also has to be radially ordered if it has to have any operator meaning. Okay, so all the previous OPs that we have written down are only meaningful if mod of z is greater than mod of omega. We will not write this r down all the time, but it's always going to be, I mean, implicit in all the things that we are going to be doing. So remember, this is radial ordering. Okay, very good. Now let's do something. Now let's try to relate OPEs with commutation relations. Okay, So let's take two fields, A of Z and B of Z. These are two holomorphic fields, and let's look at this particular integral that we have out here. So the contour actually circles in an anti-clockwise direction around this particular omega. So this operator is going to only have a meeting within endpoint functions as long as it's radially ordered. So what are we going to do? So what we are going to do is, so this is some sort of circle that we have out here, and we are going to radially order this. So we are going to pick two of these guys to, this, if you wish, could also be a larger circle, and this is going to be a smaller circle. Okay, so you can obviously deform this. So you have split this part of this sort of integral into two, as you can clearly see that if you were to sort of subtract this one from this one, then you're going to get to one here. So this means that it's a circle which is larger, and this one means a circle which is smaller. Okay, that's all. So this includes the point omega. This excludes it. Okay, so now this particular integral that we have out here is going to be split into C1 of is Z times B omega, and in the C2, since the radial ordering has to now kick in, this has to be B omega minus AZ. This is going to be nothing but A, and the commutator of A with B omega, where A now is written as the integral of AZ. Okay. So as I said, these C1 and C2 are sort of fixed time contours, one which includes omega and one which excludes it. So that's what we have out here. So we had something here which was an integral, and we have split it into two, and we have shown how this actually defines something like this particular bracket here. Okay, 4.9 is important. Okay, 4.9 is an important relation. Similarly, if you could have, so if you have two operators A and B, where A and B are now defined as the integrals of small a and small b, this is just defined by 4.11 here, and this means that so here the integral of z is around omega, and the integral of omega is around the origin. So these are things, these two equations that I try to point out, 4.11 and the previous one, 4.9, relate these OPs to these brackets that we have defined, and this allows us to translate from the operator language, from the OP language to the operator language. And so now we can, as I write here, we can translate into operator language the dynamical or symmetry statements that are contained in the OP. So in the final few minutes of the lecture today, let us try to rederive something that we have seen before. So let's firstly, remember what our conformal ward identity was. So a change in an operator O was given by the residue of epsilon z into tz into O, which is equivalent to saying that this is just the integral around omega of this guy. Now, if we define charge, conformal charge QE as the integral of epsilon z dz, then we just see from the relation that we have above I mean, that I'd shown you above, that delta of I mean omega is very clearly nothing but Q E of O essentially. So this is what, so you can go back to these notes. I'll try and put them up. But as I said out here, uh, you know, so if you have some integral like this, you can then split it up into C1 and C2, and this essentially becomes an integral. I mean, this becomes the commutator of A with B omega. Similarly here, so what we have is we have defined this Q of, as this guy, and now you can see that if you just plug this in here and do the trick that we did earlier, this is nothing but, so the delta of O is minus the bracket of QE with O. If you remember our earlier, earlier sort of definition of generators of symmetry transformations that we did, a while back, you would remember that if you have some symmetry, so let's see if I can bring this out for you. Let's give it a second. This is exactly what a definition of a symmetry was, but let's see if I can pull this out for you. So yeah, here, so you'll you see that this is what. So yeah, I mean, I don't think I defined it quite in the same way, but this is, I mean, essentially, so you would be able to. I didn't define with a commutator earlier, I guess, or maybe I did. Okay, I mean, I urge you to go back and try to actually look at this a bit more, and you would see that you would be able to define this as a symmetry generator. So this is radial order. I'm sorry. So what yeah, so this Q of E, so the change, so the ward identity actually boils down to just this. Okay, very good. Now let's do the following. Okay, let's expand out the, I mean, energy momentum tensor in the same way as we did for the fields before. So T of Z is going to be given by Z to the minus n minus 2 into ln. Remember what we were doing with these fields phi. Okay, sorry, I'm going a little back and forth. So you see, if you had a field phi of Z, you had to expand it in something which is minus m minus h, where h was the weight of the field. So when you are looking at t, in that case, T of Z is going to be summation over m z to the minus m minus 2 into something we are going to call L of n, okay? Because h is equal to 2, okay? So that's, so we are just expanding out phi. I mean, we're just expanding out t. So this is, so similarly, these ln's are just, z to the n plus 1 into t, the integral of this. Now, yeah, for example, you can try to expand out, I mean, the small epsilon as well, and then you would be able to see that q is, I mean, q is also, q is just given by epsilon n into ln. So this is by just trying to plug this back here. So you put, this is epsilon n z n plus 1, and this as yeah, I mean, as you wish. And if you plug those things in, you will find that this is equal to epsilon n ln. Okay, so that is what you will find. So next, so these are some L's which we wrote down, and let's try to find what the brackets of L's are. Okay, so what are the brackets of L's? So the brackets of two particular operators L and M are given by the relation that we have written down out here. So let's do this. So L, so this is the first line. I'm sorry. So you know, so this is going to be as we wrote down before. So let me try. So this is L, and so you have these two operators here. So L n with M is going to be given by, so there's 1 over 2 pi I squared that you get from this pieces. You have I mean, omega to the m plus 1 for for one of them, and you have z to the n plus 1 for the other, and you will have tz and t omega. So that's what you have. Now what do? We want to use the OPE here, so we use the OPE, and so we have c over 2 1 over z minus omega to the 4 twice t z minus omega squared and del t z minus omega. So we have just put in the OPE here. So now what do we have to do? You remember that this particular thing, so we are going to do the first integral on the z. So this is a pole of order 4. So you need to actually differentiate this expression. So what you need to do is you need to take this, and you need to multiply it by z minus 4 z minus omega whole to the 4 and differentiate it 3 times. So in if you do that, you know, your n plus 1 you know, is here, and then you differentiate it once more, there's an n, differentiate it once more, there's n minus 1, and at the end, so you also have to put z is equal to omega, so you get a term which is w to the power n minus 2. Notice that there is a 1 over 12 term that comes from a 1 over factorial 3 and factorial 4. No, it's 1 over factorial 3 into this half piece. So that's the 1 over 12 piece. Now for the next one, this particular term is a pole of order 2, so you are going to differentiate it once, and so what you get is just this. So you have an n minus 1 which comes out, and the last one stays as it is. So this is what the residue at the pole is going to give you. So I mean, you also notice that, you know, since it's going to be 2 pi I times sum of the residues at the poles, you have got rid of one of the 2 pi I terms. Very good. Now what do you have? You have something which is an integral over, you have a closed integral over the origin. You have an omega to the m plus 1 and omega to the n minus 2. So that is omega to the m plus n minus 1. So this is going to give you a pole only when n plus m is equal to 0. So if n plus m is equal to 0, so this is the term that you get, and so that is going to be what you have. So this is the first term here, And then so from the next term, you are going to end up with uh, you know an expression which is L plus M, because you are going to get omega to the n plus m plus 1. And if you rewrite this, and so you will see that what you get at the end of the day is an L to the L of n plus m. And there is a third term, which is the integral over omega to the n plus m plus 2 and del of t. What you have to do here is you have to transform. If you have, you have to take this, make this into yeah. So you have to integrate by parts. In that case, the first term is just a total derivative, gives you a 0 out here, and the other one is a del acting on this guy and t, right? So when the dust settles, it's just straightforward to see that this n plus m plus 2 is a term that will be pulled down, and you're going to be left with omega to the n plus m plus 1. Okay, so now what happens at the end of the day is you've already got this term and you've got this term, and from this last one you get an n plus m plus 2 into L of n plus m. And so once you add these things up, what you end up with is your Virasoro algebra. And this is, it's nice to see that everything has fit in. So this is the Virasoro algebra. This is something that we had got previously when we were looking just at symmetries and so on. Now we have reformulated this from the point of view of the OPE, and in a sense, this gives us more sort of so this gives us more clarity, and it shows us the way of looking at the OPEs, and the way of trying to look at it from the point of view of the generators of the symmetry, match up, and it's one and the same. So and you see that this extra piece that you have out here, which is something that you added onto the Witt algebra, actually comes about because you have this anomalous term in the TTOPE. So the fact that T in 2 dimensions, the stress energy tensor, is not a primary field, gives you something which is, a central term, a central extension in your, LL algebra. So this is the Virasoro algebra. This is one with the L's. There's an exactly identical one with the L bars, and L with L bar is equal to 0. So this is, now we are going to now look at things from the point of view of, we'll try and understand this a little bit more, but it's very nice to sort of see that this is, come together in this way. So that was essentially what I was looking to do in the class for today. So just to briefly run you through the same thing again, what we did is that we noticed, we said that we want to go to something which is the operator formulation, and there we looked at radial radial quantization, where since this operator formulation needed to distinguish between a space direction and a time direction, it's natural to define things on a cylinder. It's also interesting. This is something that we will discuss a little later, but it's also interesting to think of things from the point of view of string theory in the same way. And in that case also, if you're looking at closed strings, in that case, thinking of cylinders is also it's a nice thing to do if you wish. So what we can do is, if we look at the cylinder and we look at the plane to the, cylinder to plane mapping, then the equal sort of time time slices on the cylinder become circles on the plane of increasing radii. And minus infinity is mapped to z equal to 0. And once we do that, what we said is that we had this way of trying to define what the Hermitian conjugate is. It looked a little weird at first, but then we saw that these sort of prefactors and so on were required to make this inner product well defined. We also looked at these mode expansions, which are sort of like like your well-known LoRa expansions. And so once we did that, what we ended up, the next important thing that we said was the notion of radial ordering. And the time ordering, which you were familiar with earlier, gets, in this case for the CFT on the plane, gets replaced by radial ordering, which was given by this equation. And by when we were looking at this particular radial ordering, it also gave us a very natural way to interpret so things. Things like the OPE in terms of commutation relations, and we saw an integral like this by deformation of contours in this way, as we tried to show here. What it does is it defines this as as this particular commutator bracket. And once we did that, what we learned is if you have two of these operators A and B, which are given by the integrals of these holomorphic fields, small az and small bz, that can be the commutator of this can be defined in by equation 4.11. We applied all of this when we were trying to understand what how. So first we repackaged this in the language, the word identity in this language, and we saw that this QE, the change in the operator O under these conformal transformations could be just looked at the bracket of QE with the operator O. And and then what we looked at was TZ and TZ bar. And when we used our mode expansions here, we were then able to relate the OPE of ZZ bar, TT, the TT OPE, with with something that we had done earlier in the sense we could calculate the brackets of L with L, and we saw that the TTOP actually landed up on the Virasoro algebra. So this particular thing is actually extremely useful and also extremely important. It would be very helpful going forward. So I would urge you guys to just go through all that we have done in the class today. And if there are any questions now or even later, I'm happy to address them. So I'll try and put these notes up as soon as I can. But this particular thing of trying, this operator formalism fitting up with the OP is something that's important. We will use the Virasoro algebra more and more as we go ahead in the course. But this is one of the central themes of the course actually. So this was one of the central results of the course. In the sense that we have seen now in sort of the operator language what we had seen from the OPs earlier, and this is going to be useful going forward. All right, so I think I am over time. I will stop here, but if there are any questions, I'm happy to address them. Is there anything that you want to ask? All right. If not, then I will be seeing you guys next week. So, well, um, that's it for now then. All right. Let me stop sharing and see you all next week.